Hi guys, in this new opportunity we are going to solve this problem. The problem says that we have a particle that starts moving from the rest at the top of a frictionless sphere of radius r and slides under the influence of the gravity. How far below its starting point does it get before flying off the sphere? So it starts moving from the point A and moves to the point B. So the sphere, the friction between the sphere and the particle is zero. So what forces are acting on the sphere, on the particle at the point B? If we draw a free body diagram for the particle just at that point, we will have this. This is the particle at the point B. And what forces are acting on it just at that point? Well, as we know, always the weight is acting on the particle, and the weight is mg. Besides that, we have the normal force, or the reaction of the surface acting on the particle, and we have this force that is the radial force acting along the radius. We have this component is mg cosine of theta. This angle here is theta. All right, so we will see that just in a little bit. If we come back here to the initial figure, we will see that if I draw these forces real quick over here, the weight mg, this component, it would be mg cosine of theta, is because this angle here is theta by the geometry of the problem. So that's why we have this angle theta here. That's the free body. So what forces are acting, or what is the total force acting on the particle? Well, during the slide down to the point where the particle flies off the sphere, there is a normal force, this one. Remember that it started moving from the rest, v equals 0, and it started moving on this direction. So that normal force gets smaller and smaller as the particle speeds up, and at the point where the particle leaves the sphere, the normal force is 0. So just at this point, the normal force is gonna become 0. That way the particle is gonna leave the surface, and we are gonna apply the second law of Newton for this motion. So what forces are acting? We know the summation of the forces just at that point are the second Newton laws, right? Second Newton's law. Okay, so what forces are acting? We know the normal force, the component of the weight along the radius, right? The weight. Okay, so we have the normal force and this force acting to the center of the sphere, the center. This is mg cosine of theta minus the normal force that is acting in the opposite direction. Okay, remember that the second Newton's law says that the summation of the forces acting along the ratio is equal to the mass of the particle multiplying the radial acceleration. Okay, but we remember that at this point the particle leaves the sphere, so the normal force becomes zero just at that point. And because the normal force becomes zero, this equation, we are going to call this equation number 1. Equation number 1 is going to become mg cosine of theta is equal to the mass multiplying the radial acceleration. All right. Okay. We cancel the mass on both sides of the equation, and we get g cosine of theta is equal to the radial acceleration. Okay. If we clear this equation, we clear cosine of theta, we are gonna take this term, the gravity, that is multiplying, and we are gonna send it to the other side of the equation to divide. We will get cosine of theta is equal to the radial acceleration dividing the gravity. All right. Okay. Let's call this equation number 2. And we have called this equation number 1. Okay, guys. Since there is no friction between the particle and the surface, the friction is equal to 0. It's a frictionless surface. The total energy is conserved. So that means that the initial energy is going to be equal to the final energy. All right. And what is the initial energy? Okay, the energy, or we can call this equation with this energy at point A is equal to the energy at the point B. And what is the energy at point A? Okay, the energy at point A is the kinetic energy at that point plus the potential energy. But the kinetic energy is equal to 1/2 of the mass velocity squared at that point plus mass gravity, this height at that point. Okay, and the same for the energy at the point B. The energy at the point B is equal to the kinetic energy plus the potential energy. I mean, kinetic energy at point B plus potential energy at point B, and that's equal to 1/2 of the mass velocity at point B squared plus mass gravity distance at point B. But let's come back to the initial figure, and what we are gonna do is this. I'm gonna erase this real quick, and I'm gonna draw a line crossing or passing across the point B. I'm gonna call this line 0 potential energy, reference point. That means that the potential energy at this point B is equal to 0, and that is our reference point. So H is equal to 0 at that point, or the potential energy is 0. Whatever is fine. The potential energy at that point is 0. Okay? And at this point, because the particle starts from the rest, the kinetic energy is equal to 0. Taking that information in account, we have this energy is 0 and this energy is 0. So this term is 0 and this term is 0. That way we get energy at point A is equal to the mass gravity H, okay, and energy at point B is equal to 1/2 of the mass velocity squared. Let's come back to the figure again. If we see here real quick, we have, this is the radio of the sphere, right? This is the radio. And this distance is the radio too. The distance between the center of the sphere and a point at any point around the sphere. So on the perimeter of the sphere. So this distance is r. The distance between this point and this point is h. Okay? This distance between this point and the center is r minus h. Okay, guys? So this is h and v, the velocity, and this distance h. We come back here, and those are this h and this velocity. Well, because the conservation of the energy, we have the energy at the point A is equal to the energy at point B. So we have mass gravity h, or distance, is equal to 1/2 of the mass velocity squared. If we cancel the masses out, we have gh is equal to 1/2 of the velocity squared. Okay? And if we clear the velocity on this equation, we have the velocity squared is equal to 2h gravity. And we are going to call this equation number 3. Okay, guys? Well, if we remember, okay, this velocity is the velocity which the particle leaves the sphere. This is the velocity that the particle has when it leaves the sphere. And if we remember, by definition, the radial acceleration is equal to, if we remember, by definition, the radial acceleration is equal to v squared dividing the radio of the motion, in this case the circle. Okay. If we replace this equation of the acceleration in number 2 equation. Remember, number 2 equation is this. Okay, we are going to replace this acceleration into this equation. Okay, if we do that, we get that cosine of theta is equal to radial acceleration dividing the gravity, but the radial acceleration is v squared dividing the radius multiplying the gravity. In this case, this is the result. Okay, but we calculated that v squared is 2gh. Okay, so we replace this velocity into this equation. Then we get cosine of theta is equal to 2gh dividing rg. We cancel the gravity and we get that this is equal to 2h dividing r. Okay, this is cosine of theta, but we come back to the initial figure, and if we see this triangle, this green triangle, I am highlighting it. By definition, we see that the cosine of theta, by the geometry of the problem, cosine of theta is the ratio of the adjacent side to the hypotenuse. What is the adjacent side? The adjacent side is this. This is the angle theta, okay? And the adjacent side is this, okay? The orange one. And the hypotenuse is the red side. Okay, so by the geometry of the problem, or by the geometry of the problem, we have that definition: adjacent side, I mean r minus h, the orange one, r minus h, the orange side, dividing the hypotenuse, the red side, r. Okay, we are going to take this equation and we are going to replace it here, and we get r minus h dividing r equal to 2h dividing r. We cancel this r with this r because they are on both sides of the equation. So we get r minus h is equal to 2h. This h is subtracting on this side of the equation. We're gonna send it to this other side, adding up. So r is equal to h plus 2h. That means that r is equal to 3h. Well, h is equal to, this 3 is multiplying. We are going to send it to the other side of the equation, dividing. That means that we get 1/3 of r. So the distance h, where the particle leaves the sphere, is 1/3 of the radio. That's the distance. Okay guys, this is the solution of the problem. See you in a next video. Bye.